Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is soft starters. Our objective is to introduce a solid-state power electronics device known as a soft starter. Soft starters reduce inrush current and modify acceleration and starting torque characteristics. This lecture operates under the assumption you've watched the primary resistor reduced voltage starters lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. As you are no doubt sick of me reminding you, the direct and instantaneous application of full voltage to a motor at standstill produces a tremendous surge of current known as inrush. Although brief, inrush current can place an unnecessarily high demand on the electrical distribution network, and industries often pay a financial penalty for such events. Additionally, the abrupt acceleration of a motor from standstill may damage the mechanical linkages like belts, chains, shafts, gears, and couplings the system uses to manipulate the applied load. It is for this reason reduced voltage starting methods are employed. Reduced voltage starting methods include, but are not limited to, electromechanical means like primary resistors, part windings, Y-start, and delta run starters, and solid-state means like soft starters and motor drives. All these methods serve to limit inrush current and limit mechanical stresses to the driven load. Today we'll discuss one of these methods, soft starters. Soft starters are astoundingly different from the primary resistor, part winding, and Y-start delta run reduced voltage starting methods we've previously discussed, because they are solid-state power electronics devices composed of no moving parts. Solid-state soft starters offer inherent advantages and come with their own peculiarities. Recall that the electromechanical means are all characterized by a clear and definite transition from start to run mode. For a primary resistor reduced voltage starter, either the primary resistors are in or not in the circuit. For a part winding reduced voltage starter, either part of the windings are connected to full voltage or all of them. For a Y-start delta run reduced voltage starter, either the motor is in Y configuration or delta configuration. There is no in-between stage, and the starter never makes a smooth, gradual transition from start to run. Really, the only time we ever saw an attempt to stage the transition between start and run mode is using a primary resistor reduced voltage starter with two banks of primary resistors. Even so, this is still a stepped approach, and the graph of inrush current would show noticeable disjoints during the transition periods. Doubly so for Y-start delta run reduced voltage starter, since this is an open transition method in which the motor windings are briefly de-energized between start and run mode. The open transition would be characterized by an undesirable transient spike. For this reason, soft starters are employed. A soft starter, among its many abilities, can smoothly ramp applied voltage from a predetermined start value to full voltage over a customizable period of time. This smooth voltage ramp yields more precise control of starting current and torque. Additionally, soft starters are often smaller, lighter, longer lasting, easier to adjust, and more efficient than their electromechanical equivalents. For the purposes of this lecture, we're going to largely ignore the solid-state components inside a soft starter that make these advantages possible and treat the soft starter as a box full of black magic. For those interested in delving into the dark arts, stay tuned, because later lectures on power electronics devices at the Big Bad Tech channel will go into nauseating detail about diodes, transistors, SCRs, triacs, and more. Long story short, it's complicated, and I want to keep this lecture manageable and concise. Most soft starters have the following user-adjustable characteristics: starting voltage, ramp-up time, and ramp-down time. More advanced soft starters may also include the following additional features: kickstart, current limited start, and constant acceleration. We'll briefly discuss each of these aspects. The starting voltage is ordinarily expressed as a percentage of full voltage. This is the starting voltage at which a soft starter initiates conduction to a motor. Ordinarily, soft starters should avoid going below around 40% of full voltage, since anything less may not produce the current necessary to even move the rotor. The ramp-up time is the period of time it takes for the soft starter to steplessly increase the voltage from the starting voltage to full voltage. The smooth, gradual nature of the applied voltage during the ramp-up time means there is no large current surge or sudden acceleration when the motor is first started. Additionally, some soft starters allow the ability to soft stop a motor, whereby applied voltage is not instantly removed from the motor, but rather steplessly ramped down to 0 volts over a period of time. The longer the ramp down time means the longer the deceleration period. Note, ramp up time is the positive going period from starting voltage to full voltage, and ramp down time is the negative going period from full voltage going down to 0 volts. Note the different start and end points. This is an excellent quiz question, and you'd look terribly stupid blowing something this easy. This particular graph shows the soft starter upon being enabled starts at 40% of full voltage upon receipt of an input signal. If this is a 120 volt line to neutral or 208 volt line to line light industrial 3-phase AC system, this would mean the starting voltage is 48 volts line to neutral and 83.2 volts line to line. This graph illustrates the soft starter would take 10 seconds to ramp up the applied voltage from 48 volts line to neutral, 83.2 volts line to line, to the full 120 volt line to neutral, 208 volt line to line upon receipt of the input signal. The graph illustrates the soft starter would take 10 seconds to ramp down the applied voltage from full voltage to 0 volts upon loss of the input signal. This particular soft starter has 3 adjustable potentiometers to respectively adjust ramp-up time from 0 to 20 seconds, start voltage from 0 to 100%, and ramp down time from 0 to 20 seconds. Again, note, ordinarily soft starters avoid going below around 40% of full voltage, since anything less may not produce the current necessary to even move the rotor. While we're taking a look at this particular soft starter, note the 2 indicator LEDs, ready and run. Since soft starters are solid-state devices, it's impossible to tell if they're enabled, unlike an electromechanical contactor or relay that physically moves when the coil is energized and is accompanied by a characteristic sound. It is for this reason soft starters often use indicator LEDs. The ready light remains illuminated when the device is powered up and ready for action. The ready light blinks upon being enabled and continues to blink during the ramp-up period. The ready light turns off and the run light comes on when full voltage is applied. Finally, during the ramp down time, the run light turns off and the ready light blinks until 0 volts. The ready light remains illuminated and the soft starter is ready to initiate another ramp-up event when enabled. These indicator LEDs are often invaluable troubleshooting resources. Advanced soft starters may also offer the ability to kickstart a driven load by allowing a brief initial boost of current at startup to break away loads with a large static inertia. This kickstart provides a current pulse for a selected period of time. The 2 remaining aspects of advanced soft starters, current limited start and constant acceleration, necessitate more involved circuitry in the form of a feedback mechanism. A current limited start sets a user adjustable limit to current during the ramp-up time. If during the course of the voltage ramp-up, the soft starter hits this upper current limit, it lets off the gas to keep current below the ceiling. This could be used to establish a predictable maximum current draw for variable applied loads at starting. Constant acceleration mode necessitates feedback from a tachometer, which if you'll remember from the mechanical power, torque, and speed lecture available at the Big Bad Tech channel, is a means of measuring rotational speed. The rotational speed transducer updates the soft starter with the speed of the rotor, and the soft starter can back off or step on the gas for the ramping voltage accordingly to keep acceleration inside a given range. This closed-loop control feature allows the soft starter to govern the physical output of a motor. Note this feature borders the traditional boundary between soft starters and motor drives. This begs the question, what is the difference between a soft starter and a motor drive? My answer to this question is simple. Soft starters govern the starting and sometimes stopping characteristics of motors, whereas motor drives govern the starting and stopping aspects as well as the running characteristics of motors. This is to suggest that most motor drives also have adjustable start voltages, ramp up, and ramp down times to govern the starting and stopping characteristics of motors. This lecture, therefore, serves as an introduction to motor drives. As we'll learn in later lectures, motor drives vary applied frequency and voltage during the run stage to govern the output speed and torque of the driven load using advanced closed and open loop control.